Welcome to chapter 5, Stereochemistry. We're going to talk about the 3D structure of the molecules, but first we need to know some terminologies in this chapter. First about the configuration. What is a configuration? That's a 3D arrangement around the atoms, especially the carbons, since we study organic molecules. And so stereoisomers are different isomers based on the 3D structure. Okay, so stereoisomers have different 3D structures. But what type of molecules we are going to study in this chapter? The ones that we call chiral molecules. Chiral molecules are the ones that are not superimposable on their mirror images. But let's first talk about superimposable. What do we mean by superimposable? In our body, we have some parts which are called superimposable mirror images. Let's talk about the handedness, about the hands. When I talk about the handedness, let's imagine that I'm talking about the mirror images. So my two hands are mirror images of each other, right? They are all mirror images, the fingers and the palm. But when we say superimposable, means that we can overlap them on each other. Are my hands superimposable? My pinky goes on my thumb, my ring finger on the index, and same here. The only two fingers that are superimposed are middle fingers. So my hands are mirror images, but they are not superimposable on each other. That's what we call handedness. So the same as the two sides of our body. If we consider a mirror image in the middle of our body, the two different sides are mirror image, but they're not superimposable. They're different from each other. So that's a quick study of these terms. Another term we need to know here is enantiomer. Enantiomer. Just like our hands, What did we just say about our hands? They are mirror images, not superimposable. Oops. Not superimposable. All right? So, first we talk about enantiomers. The molecules, let's go back to chiral molecules and chiral carbon. First, we need to talk about chiral carbon. A chiral carbon is a carbon attached to 4 different atoms or groups. Like, let's say you have carbon connected to chlorine, to hydrogen, to bromine, and to CH3. You see, 3 different groups and atoms are connected to the central carbon. So this carbon is called chiral. And we normally show the chiral carbons with the star on them, the little asterisk. So far you know about chiral carbons, and you already know this representation of molecules from previous chapter. Again, to remind you, if the black atom is the carbon atom, the atom towards your face is, let's say it's bromine here, if you want to use the same molecule. And hydrogen is in the back, away from you. And and you see the chlorine and CH3 on the plane. Okay, so that's how you put bromine on wedge and hydrogen on dash. That's the representation. My suggestion is that if you have if you want to get the molecular model kit, you can easily get it and play with it until it helps. It helps for the visualization of the molecule. Okay, now let's draw the mirror images of each compound on page 1 of this study guide. I will work on one of them. Let's say we're working on A. A mirror image. Imagine you have a mirror here, and then mirror image is carbon is here, chlorine. Then you have another group. Then you have bromine closer, and another group to the back. That's the mirror image of this molecule. If we want to locate the stereogenic centers in the following molecules, let's pick, doesn't matter which one, let's pick amlodipine, the first one. I'm not going to draw all of them and work on all of them, but let's work on the first one. Okay, this is the first compound. We are supposed to work on the stereogenic or chiral centers. Another name for chiral carbon or chiral center is the stereogenic. So they are all the same. Chiral carbon, chiral center, and stereogenic center. They are all the same. Okay, what was the condition for a stereogenic center for a chiral center? The carbon is connected to 4 different groups. And learn something now. When a carbon is connected via a double bond, a carbon-carbon double bond, it looks like carbon is connected to 2 carbons with single bond. Okay? That's the rule. Whenever you see a carbon-carbon double bond, means that carbon is connected to 2 more carbons via a single bond. So, none of these carbons with a double bond can be stereogenic because they automatically are connected to 2 similar atoms, 2 carbons. So, none of them around this ring is stereogenic. The same for carbon-oxygen double bond. Carbon-oxygen double bond it looks like carbon is connected to 2 oxygens. So this carbon is also not a stereogenic. These carbons are not a stereogenic. These carbons are not. But how about this carbon? One connected to this group, another one connected to this side of molecule, and this one another side of molecule, and the 4th bond is definitely hydrogen that is not shown, right? So since this carbon is connected to 4 different groups, you put a little star or you circle it, but I told you the rule is to show the chiral center or stereogenic center with a star. These carbons of double bond are not, carbon of double bond not. This carbon is connected to 2 hydrogens, so not. These are the same, the same, the same, and this carbon is connected to 3. So such a huge molecule only has one stereogenic center. Go ahead and do the same for the rest of the molecules on page 4 for zopiclone and for Tamiflu. These are familiar names, right? Okay. Another quick practice on stereogenic or chiral centers is I wish you were with me to tell me which one you would like to work on. Let's work on C first. We'll work on a couple of them to give you an idea of how to work on the rest. Okay, so in this practice exercise, we need to locate the stereogenic centers. Again, locate the chiral centers. The carbons of double bond automatically are off the pictures. These carbon, 1, 2, 3, the 4th one is the hydrogen. So this is my first stereogenic center. This carbon is connected to this group, and 2 similar CH3 groups. So it's not a stereogenic center. This carbon connected to this side of molecule, an OH group, and the 4th one is a hydrogen. So this is my second stereogenic center. And let's work on E. Hope you're able to see. Let me change my marker. Okay, let's determine the stereogenic centers. This carbon connected to a CH3, this side of molecule OH, and the 4th one is a hydrogen. So this is the first stereogenic center. This carbon, the same story, this side of molecule, a CH3, and the last one is hydrogen. This carbon is connected to 2 hydrogens, right? It's missing 2 bonds, so this cannot be a stereogenic center. This side of molecule for this carbon, this side of the molecule, and CH3, so this and last one is hydrogen, so this is another stereogenic center. This carbon is connected to OH, a hydrogen, but the 2 sides of molecule are exactly the same, right? So this carbon cannot be a stereogenic center. This carbon can be because the 4th one is a hydrogen and these 2 sides are different. This carbon is connected to 2 hydrogens and this is going to be the last one. Okay? I'm sure you can determine the rest of them on this page. Let's talk about page 3. We're moving to page 3. how to draw stereoisomers. There are two ways. By using the mirror image, as we did, or inverting the configuration on chiral carbon. As an example, let's draw 2-butanol and then draw the 2 isomers. What I always do and I recommend you to do is to draw the line bond structure first. 2-butanol is this molecule. OH group is on the second carbon, that's why it's called 2-butanol. So let's determine the chiral center first, because it's in enantiomers, the stereoisomers are all about chiral carbon. Which of these carbons is connected to 4 different groups? I'm sure you would say this one. So at this point, doesn't matter how you distribute the groups, just distribute them whichever you want. I put hydrogen in the back, I will put OH in the front, I will put CH3 on top and CH2CH3 on the side, right? Because this carbon is connected to a hydrogen, and OH, a CH3, and a CH2CH3. So I have distributed everything around this chiral carbon. The first method is use the mirror image. So if you use the mirror image, CH2CH3 is closest, right? Then CH3 is still on top, hydrogen is the farthest, huh? And you have OH on the wedge. Correct? This is the first method. The second method is to invert the configuration. Allow me to, since I don't have enough space, to just keep this. The same molecule. I'm just inverting the configuration, means do not use the mirror image. Just keep 2 of the groups on their place. Doesn't matter which groups. You can switch these 2 groups, or you can switch these 2 groups. So you can say OH goes to the back now, and hydrogen goes to the front. And to show you that you could have used the 2 other groups, let's draw the other group also, the other molecule. I wish I left some space. Okay, fine. You see, I switched CH3 and CH2CH3, and I keep OH and H on their own place. I just want to show you that you can switch any 2 groups to go with the second method. Now, let's work only on one of these practices here, and I'm sure you can work on the rest. I'm working on A. The procedure will be the same for B and C. And you know, if you have any question, you can always ask. All right. All right, so the first method using the mirror. In the mirror, OH is the closest, right? Then you have oxygen. Then you have this carbon. Hydrogen is still on the back, but closer this time to the mirror, NH2 still on the front but farther from the mirror. You have this, and OH groups haven't changed their place, but they're farthest still. Okay, that's the mirror image. Now, what if we want to use the second method, inverting the configuration? Which one is the chiral carbon? This one, of course. It's connected to 4 different groups. Don't forget, we can only play with the chiral carbon. And what did we do to invert? We just switched the location of our groups, right? That's the second method. Do the same for B and C. Super easy. Okay. Now, we are going to name or to label our chiral carbons. You remember we talked about cis and trans before. Now we are using another type of stereoisomer labeling. We call them R and S configuration. We are going to determine the configuration of chiral carbon. Determining configuration of chiral carbon. All right, ready? Imagine, I just go with numbers now, just like what you have on page 4. Let's say we have a carbon here, a group, numbering system like this. So let me talk about this first, and then I will change these numbers with actual groups and how to determine which one is group number 1, which one is 2, which one is 3. Then, if we have 3 situations, first, if group 4 or least prior group in the back. That's the easiest situation. You determine rotation from 1 to 2 to 3. If it is clockwise rotation, you call it an R configuration. If it is counterclockwise, it's called an S configuration. So let's determine it for this particular molecule we have here. You see 4 is already in the back. You see it on these dot lines or on the actual dash lines. So let's determine the rotation from group 1 to 2. From 1 to 2, 2 to 3. What is the rotation? It looks like a steering wheel, right? The rotation is clockwise, so it's an R configuration. It's an R carbon. That's how you label it. The second situation, if the least prior group or group number 4 is in the front. By the way, this is my way. These are my ways, my shortcuts, so that I find it easier to deal with. If group 4 is in the front, then my way is determine rotation from 1 to 2 to 3. If you see it as clockwise R, it's actually S. Why do I say that? Because our goal is always to push the least prior group to the back. But if the least prior group is in the front, means that we need to push it to the back. I told you, this is my way, my shortcut. If I keep it this way and determine the rotation from 1 to 2 to 3, 1 to 2 to 3, it looks like R, but group number 4 is in the front. If you actually push it in the back, to the back, the rotation is going to be S. Let's push it to the back so you will see. If I hold 2 in my hand and push 4 to the back, what happens? 4 is going to the back, right? 2 is in my hand. So 3 comes to the front and 1 goes to the place of 3, right? Oops, what did I do? Okay, 1 is here. Sorry. 1 is here. 1 goes to the location of 3. So now rotation from 1 to 2 to 3 is what? Counterclockwise. So I'm cutting this step for you. Instead of rotating it and getting stuck within the rotation, I just want you to determine the rotation as is and then switch the letter. So if it is clockwise, it looks like clockwise, but it's actually counterclockwise if you push group 4 to the back. But you don't have to push it to the back. Save time, energy, and confusion. So just determine the rotation as is and switch the letter. If it looks like clockwise, it's actually counterclockwise. So R changes to S. If it is counterclockwise, so it looks like S, but it's actually R. I'll work on different molecules with you. And finally, the last one that I unfortunately don't have a shortcut for. If group 4 on the plane push 4 to the back and determine rotation. Okay, like let's say all right, so where is the least prior group? Group 4 is on the plane. So as if like I am holding the other group on the plane in hand and pushing 4 to the back. So let's do it. 3 is in my hand. I'm pushing 4 to the back. What happens? 2 goes here and 1 comes to the front, right? Just a little bit to push 4 to the back. So 2 goes there and 1 comes to the front. So now determine the rotation. 1 to 2 to 3, it is S. So for situations 1 and 3, you don't have to switch the letter. Only when group 4 is in the front, switch the letter. You can do it for all of these examples on page 4. And now it's time to switch these groups to actual groups and show you how to determine the priority. Priority is by atomic number. Priority is atomic number. Pay attention. Atomic number, not atomic mass. Atomic number. So if you want to determine the priority between CH3 and Cl, which one has a higher atomic number? carbon, by the way, if you have CH3, we're just talking about the first element. Which group has a higher, which element has higher atomic number? Carbon, number 6, or chlorine, number 17? 70, right? Chlorine. So chlorine has higher priority. One more thing. If I have two similar groups like CH3 and CH2CH3, let me draw it as open as I can. CH3 and CH2CH3. We go, this side is the connection to the rest of the, to the chiral carbon. So we go atom by atom. Carbon and carbon are the same so far. Here, if you go one step further, you have a hydrogen, but you have another carbon. Between hydrogen and carbon, which one has a higher atomic number? Carbon. So if you get a tie, you have to get further from chiral carbon until you find your tie breaker. Okay? So, and the last one, as I told you before, when you have carbon-carbon double bond, it looks like carbon connected to two carbons. Or if you have carbon-carbon triple bond, as if you have carbon connected to 3 carbons. So multiple bonds are equal to the same number of bonds. Now, before finishing this video, if we want to work on determining an actual molecule, let's say you have chlorine, you have hydrogen here, if you have CH3, and you have CH2CH3. Among all of these, hydrogen has the lowest atomic number, 1. So it's always group 4, if you have it. Chlorine, carbon, carbon. Chlorine has higher atomic numbers, so this is group 1. Between these two, what was the rule? Carbon and carbon are the same, so let's move further. 3 hydrogens, but 1 carbon. So carbon is prior than hydrogen. So this is group number 2, this is group number 3. We are trying to determine the configuration R or S. Let's see how we can determine it. Hydrogen is already in the back, so we're dealing with the first situation. If it's in the back, we just need to determine the rotation from 1 to 2, 2 to 3, and it's clockwise, so it's an R configuration. Okay? And we will work on more in the next video.